process. So the first thing we need to do is we need to create a cell membrane. And you guys all lined up so nice. This is lovely. Okay, so the first thing we need to do is we need to create a membrane. Okay. Now a membrane has got two ends on it. Okay. So take, and hold that. Okay. Sarah, hand up, tape it to the floor. Okay. Okay. Now, we're going to do the same thing on the back, yes. Okay, so we're creating a double membrane organelle. So, both of those phospholipid bilayers. So, I love lab tape. Okay. That's okay, it's all plastic. Oh, grab that, tape it to the ground. Okay. This part in front is the thylakoid space. Okay? In back is the stroma. Okay? Everyone with me on this? Okay. So what we need to do is these ladies are going to act out the roles of these molecules. Okay? So one of the first things we're going to do is we're going to assign a water splitting enzyme. So Hannah here is going to be the water splitting enzyme. I even have signs. I know, super exciting. So here's a molecule of water. What's in a molecule of water? An oxygen, which that was called, okay? And two hydrogens, okay? A proton, that's the orange, and an electron, that's the white, okay? So I have two of these in my box. So what the water splitting enzyme is going to do, and the water splitting enzyme actually in the thylakoid space, okay, is she is going to open these up. The electrons are going to, actually I got it backwards, the electrons are orange, the protons are white. The electrons are orange, the protons are white. And so what's going to happen is she's going to take the electron and it's going to get passed down the line, okay? The protons actually end up staying in this thylakoid space. So we're going to have like a little bucket here, okay, down front where she can drop them. Now the oxygen, I have to wait until I open another one to have two oxygen molecules, gives me a molecule of oxygen gas. In theory, plants are actually going to open these pores called stomata, or in the case of our little leaf discs, they're going to float out of the edges of the leaf discs that have been cut. And so I could like throw these out the hallway. They generally frown upon me throwing things out of the hallway, so I have this bin down here. It's going to be for our oxygen. Okay? Again, I'm going to hold that. Now, the next thing that happens is that electron is going to be donated to the empty space in the reaction center. Now, if I had a lot more people, Olivia here would have some friends. Okay? Sorry, that sounded way worse than that. Sorry. Okay, so would she would be surrounded by individuals who were accessory pigments. Okay? And so as they were collecting those photons of light, they'd all be funneling it in to Olivia. Okay? That's what I'm pretending to do here. Okay? And so her electron goes from being like this.
Yeah,
Okay.
I know.
Then you'd be like, woo! Okay, it's Friday morning, weekend, okay? And so we get that energy, okay? That gets the electron so excited, okay, that it actually leaves that space and goes to the first electron acceptor, which is Shannon. She's going to be plastic quinone, okay? Plastic quinone, like our reaction center, are embedded in the membrane. So they're standing between the two yellow lines. Okay? Plastic quinone takes that excited electron and passes it to the B6F complex. Okay? That's Anastasia. Okay? Now Anastasia has two jobs. She's the acceptor for that electron, but she's also going to move a proton. So I'm going to actually put an empty bin here between Hannah and Anastasia. And then I'm going to take this bin with some extra protons in it and put it behind Anastasia. She's going to be taking protons from the stroma and moving them to the front of the room, okay, into the thylakoid space. So far, so good, everyone? Everyone okay? Okay. The final electron acceptor in this first train is Carrie, and she is plastocyanin. Plastocyanin is actually just inside the membrane. Okay, just inside the thylakoid space. Hanging out right there. Beautiful. Beautiful. Okay? She is our final electron acceptor, and now the energy, instead of being up here, is down here. So carries me on Monday, okay? So now what we need to do is we need to get that electron charge back up. So we're going to pass that to our next reaction center. That's Taylor. So now Taylor gets that electron, and we're going to send some more light again. We'd have some friends here. Sorry, Taylor. And we would be funneling those photons of energy in towards the reaction center. And woo, we're back up here. It's Saturday now. Woo, okay? Everyone good? So that's so much energy, it leaves that reaction center, okay, and goes to our next carrier, which is ferredoxin. So Nicole's ferredoxin, okay? She takes that molecule, and she donates that electron to NADP reductase, okay? Kylie, okay? Kylie has back here, okay? And ferredoxin, actually, you're going to step back here, Nicole. She's actually on the other side of the membrane. She's closer to the stroma, okay? Kylie has some containers, okay? Thanks, Gary. Sorry, I'm short. Okay, so these are labeled NADP plus NADPH. So in order to turn these from NADP plus into NADPH, what I need to do is have Kylie open up, NADP reductase opens the container and drops in one electron, then one proton taken from the stroma, okay? So Nicole, you can help her with that, since, you know, I gotta put this over here too, okay? And then adds one proton and one additional electron. So 2 electrons, 1 proton. Everyone together. 2 electrons, 1 proton. I feel like I'm toasting here. Okay. So once that is filled, that's an electron carrier that can go off and do work. Okay? So now we've got all of our proteins doing their thing, all of our membrane-bound proteins doing our thing, but we don't quite have that gradient evened out. So we're going to take advantage of the fact that we end up with this proton gradient, okay? And we're going to use that to make ATP. So, Sarah and Marissa down here, since this is something that requires multiple hands, I'm going to have you guys do this together. Okay? They are going to be ATP synthase. We'll just pretend one of you is the umbrella part and one of you is the tunnel. Okay? Okay, you can be the umbrella, you're the tunnel. Okay. So what I have here are ADP molecules. Okay? Inside are 2 of these little orangey colored phosphate groups. Okay? ADP, adenosine diphosphate. In order to create a high energy molecule, I need to add that additional phosphate group, which is just a phosphate with some oxygen attached to it. Okay? So, what they're going to do is they're going to take some protons from the thylakoid space, okay, and funnel them back into the stroma. Okay? And as we funnel them back into the stroma, as they're moving those, they can take some high energy phosphates, they are this awesome yellow color, okay? Add them to ADP to make ATP, okay? Everyone clear on how this is going to work? Okay. So ladies, my job is to make sure there aren't ping pong balls all over the floor, okay? So I'm going to be roaming around in the front here, help each other out, okay? When I say go, we're going to start this process. Now, seniors, if at any point you cannot do your job, what do? Yell
for help.
Yes, okay. They're going to yell stop, okay? And we're going to stop the process and we're going to talk about what happened. Cool? Okay. We're good. We'll pretend that you started the process. Okay.
With 2, right?
Well, don't worry. Remember, oxygen's going to collect and then they're going to bond together. Okay? So, remember, we can only pass one electron at a time. So one orange ball can be in your hand at any one time. Okay? Right? Okay. Is everybody ready? On your marks. Get set. Go. Ladies in the audience.
Get excited.
You need to be watching what they're doing. Start another one. You can start another one. So once Olivia's hand is empty, Hannah can start another one. Those go in your bin. Okay?
Woo, hot water.
Keep going. So they're taking that electron, it's getting excited, it's going to phosphoquinone, it's going to B6F, it's going to paradoxin, back to be energized, making ATP. Yep. No, you can just keep going. Okay? Is everyone keeping track? Follow those electrons, ladies in the audience. Talk it out to your neighbors.
Alright, we got another one.
Watch all the processes moving.
Oh, stop.
Okay. I was told that they need to stop. What happened? Okay, so there are no more protons in the stroma. Was that what you were going to say?
Yeah.
Awesome. Okay. So, what do I need to do to move protons from the thylakoid space to the stroma? You ladies, look at the diagram. How do I move it? I heard some people muttering, yeah. I have to do the ATP synthase. So here's what I'm going to do. I'm going to come over here and let these ladies make a couple molecules of ATP. So make a few molecules of ATP. Oh, that's part of the problem. Those need to go in the gradients. They don't go in the buckets.
Wow. That would be the issue.
Yeah. Okay. We have a dysfunctional ATP synthesis. You put them in there, Nicole. Okay. And then that way they can be taken from back here and pumped across. Okay. So now that we've got some protons and we've evened out the gradient a little bit, we can restart the process. Yes?
Yep.
Okay. So start it back up. Okay, remember, you guys in the audience need to be following bouncy balls. Stop. Okay. What do we do if we lose the protons again? What do? ATP, okay. Do your So you can see, if you get any one part of the process that slows down, it changes the rate at which we're making those electron carriers, okay? That's okay. That's the way all biochemical processes start, okay? Continue, ladies. Talk it out, ladies in the audience. Talk it out, ladies in the audience. What do you see?
Stop it.
What do you want from me?
We need to work in harder. Wait.
What are we doing?
Okay.
What are we doing?
Yes, you can. Take it through your 4. Okay. Stop. Okay, so we are out of NADP containers. Okay? What's that mean? Ladies in the audience. What can I do any more work in this process if I'm out of carriers for electrons? No. So what might I need to do? I need to use it, okay? So what I would do is I would take these NADPHs and move them from point A to point B and use them up in some of the processes we're going to talk about on Monday, okay? Once I empty out those carriers, then we can suddenly restart the process. So when we run out of carriers for those electrons, we can no longer run the process of these light-dependent reactions. Okay. Hannah, you're on your last water, yeah? Okay. So if I run out of water, can I do photosynthesis? No, I cannot, okay? So what I would need to do is bring more water into the tissues that are photosynthesizing. We're going to talk about how that works next week, how we get water to the places where we do photosynthesis. Sarah, are we just about out of ATP?
We just actually.
They made their last molecule of ATP. So we need to use up that ATP, turn it back into ADP, so that we can continue the process.